You're going to have more people coming in, do you know, or? Fair enough. Okay. Okay. This is Rahul's class. Okay. Okay. So let's get started. Let's post the notes anyway. They can look it up. So we saw, what did we see so far? Let's recall the statement of the multiplicative. Guarantee. Basically showed that for any fixed distribution P on the n experts, the cumulative expected loss of the multiplicative weight update method with parameter epsilon, called LT. This is defined to, this is MTPT. MT is the loss vector that leads step. PT is the probability with which the algorithm is behaved. This is upper bounded by the corresponding vector for the corresponding loss for the fixed distribution plus epsilon times P plus ln n by epsilon. That's what we had shown. And furthermore, this term, so this is the key thing which we have. In this term, this came because we assumed we were starting with the uniform distribution and doing it. If we had started with some other distribution, can be refined to the divergence between P and if we had started with some starting distribution by epsilon, if P1 is the starting distribution. It seems this. It was a very generic method with this one. What we'll see today is two very specific applications. We will see applications towards here. We started one application last time, the zero sum game. Last time by mistake I mentioned Nash equilibrium. Zero sum games are different from Nash equilibrium. We'll talk about zero sum games, computing the value of zero sum games using this. It will give you a far more efficient way of computing the value of zero sum games than otherwise known. And in machine learning for boosting. These are two different applications we'll see today. And in the next lecture, we'll see possibly two more applications of it. So we're going to from now onwards see applications of this. The first application will be to approximating zero sum games. So what's the setting here? We did this in detail towards the end of last lecture, but let's quickly remind. There are two players, which we'll call the row player and the column player for complete lack of creativity. Call them these two players. And the row player has certain number of strategies, say n strategies. It's an n by n matrix. A role player has m strategies, and the column player has n strategies. These are the strategies they have. And each time they play a strategy, we have a matrix which tells you it's a zero-sum game. So if the role player plays a particular strategy and the column player plays a particular strategy, we have a matrix we have an entry which tells you how much does the role player play to this one. So we have a payoff matrix. We are given as payoff matrix. And this is a zero-sum game. It's how much the row player gives to the column player. So we're given this massive. Think of m and n as very large quantities here. So this is m here. This is n. And aij is the amount paid by a row player to column player when they play strategies I and j respectively. And this set of mn are called pure strategies because these are the original set of strategies called. We can also have some things which are called mixed strategies, and these typically refer to probability distributions over m and n. Okay. And because this matrix sort of talks about how much row gives to column, the column player wants to maximize his payoff, and the row player wants to minimize the amount he wants to give it to the column player. So we had defined these quantities CP. So P is a mixed row strategy. If the row player is going to play the mixed row strategy, see, CP is going to be defined as the max overall j and n of API, where API itself is defined as APJ, sorry. APJ itself is the expected value of AIJ when I pick I according to it. So if the row player is playing strategy P, big strategy P, the column player is going to play strategy J. He wants to maximize this. So what the row player will try to do, the row player will play a P that minimizes this quantity. The row player would like to play a mixed strategy which is minimum of CP. And similarly, we can define if Q is a mixed column strategy. We can define RQ with a max over, sorry, the min. And what? These are things we'll study in detail later on in the course. In modules Piyush will be teaching. Weak duality will tell us that for all P and Q, RQ is always less than or equal to CP. So in other words, this line looks like this. There is Any PCP looks over here, RQ looks over here. So in particular, the P that minimizes this is always larger than the Q that maximizes this. So these are two different things. So P star and Q star. So let's call P star to be the arg min of P CP, and similarly Q star to be the arg max Q of RQ. Weak duality will just tell you that on the number line, CQ star is somewhere over here, RQ star, sorry, CP star. That they are in this quantity. There is RQ, which is less than RQ star, which is then CP star and CP. You have it this way. Strong duality will actually tell you. We are not going to prove strong duality. Strong duality is a powerful theorem of its own. We'll be proving later on in course, which tell you that actually these 2 points are actually the same point. Strong duality says there exists lambda star such that RQ star equals CP star equals lambda star. So this is all 1 point over here. The point is lambda star. We will be assuming the duality theorem. What we want to do, we'll be assuming duality. We'll assume that there is such a point. What we want to do is, so given any payoff matrix, there's always lambda star, which is a von Neumann min-max equilibrium point. What we want to do is we want to find out this point. That's the goal of this one. We won't be able to find it exactly. We'll give a very efficient technique to find it approximately. That's good. We'll assume. So what the goal is going to be assuming strong duality. And the existence of an oracle, say, that on input a mixed row strategy P outputs J such that A Pj equals Cp. The goal is we need to given assuming this, want to compute lambda star, P star, and say Q star with utmost delta error. Okay, that's going to be our goal. We'll assume the strong duality is not a theorem we're going to prove now. We will be proving it later on when we do LP duality later on in the course. Assuming LP duality, notice we're going to work in a case in which this matrix is too large for us to sit and write down. So M and N are too large. So our only access to this matrix is I give you an algorithm which, when given a mixed strategy P, output tells me what is the best row strategy, column strategy that attains CP. Suppose that's how I have access to this matrix. I have access to this matrix. From that algorithm, we are going to try to find. Of course, if I had the matrix explicitly, I can find this out myself. But we're going to say that suppose I had access only to the algorithm, with how many calls to this algorithm can I actually compute lambda star, p star, q star with good enough? So what will we do? We basically what we'll try to do, we will try to compute lambda tilde, p tilde, and q tilde such that they all satisfy the following. Lambda tilde is it will be larger than lambda star, but not too much larger than it. CP tilde. CP tilde, notice that it has to be always greater than CP star. CP star is the smallest of them, but we'll ensure that it is no more than CP star plus delta. This is lambda star plus delta. So P tilde will be some other mixed strategy which will be very close to P star. And similarly, that is fine. P tilde will of course always be less than RQ star. But our goal will be to have it to be not too small compared to RQ star. Okay. So we're going to set this up as an expert's game, run it for a certain number of rounds, and using that, we are going to get. So how do we, so setup. So we are going to assume for the end setup, the n experts. I think I should have flipped the m and n. Let me flip the m and n. This is m, this is n. That's n strategies and that is n. Keep it to this one. The n experts will be the n pure row strategies. Therefore, each time the game is playing, the game is going to be playing a probability distribution over the row strategies.
Could you go over the oracle again? The oracle that we are using.
The oracle is just this. The oracle. Let's write down the oracle. The oracle is oracle. I give it a P and it outputs J such that APJ equals CP. Okay. That's the oracle. The oracle, when you give it a P, it outputs J for us. And now I have to set it up. There's an imaginary MWM setup I'm going to think. What's the MWM setup? I'm going to think of it as the n experts in the MWM are actually the n pure row strategy. So each row is going to correspond to one strategy. And each time the game is playing according to some mixed strategy. It's a probability distribution of the n experts. So each action of the game is a distribution on n experts, which is a mixed row strategy. So this is the teeth action will be PT, which will be the mixed. At the teeth step, you'll be playing this. So initially, we'll start off with the uniform distribution on the row status, and then we keep changing it. It will be PT. And what's going to be the action? What's going to be the outcome? The outcome vector basically will be when you play PT. When you play PT, you're playing PT. That is some distribution over here. There is a best column response. And that's going to be the cost vector for the column response. Thing which I didn't mention is this AIJs. We are going to assume that the payoff is bounded. I need that for this proof.
The Oracle is not giving us all the AIJs, right?
The Oracle is not giving us all the AIJs. The Oracle, if you play a particular P, it will tell me that vector JT. It will tell me a particular column.
The whole column.
Actually, all I want, no, I need to know the whole column. I need to know the whole column.
Okay.
Because I will need to do the whole column to update. The way I'll do it is because you'll just see the way the algorithm goes is we will assume that the Oracle now, the Oracle on input PT, say outputs JT. It outputs the best response, the corresponding the JT. It's a column index. And then we will set empty exactly to be that particular column index. It's a cost vector apart. So I would need to know. So the Oracle you're assuming gives you actually this whole column. So empty, this vector empty, sorry, this not this vector, the vector empty is rather it's a transpose of this object. Okay. That's going to, and that's all. Once I've said this, now you can run the game. So let's just run the game for capital T steps. On with above experts and cost vector for capital T steps. Okay, so we got the algorithm is going through and we're starting with the uniform distribution. We want VU of so it goes to a sequence of P. We're starting with the uniform distribution. It goes to P2, P3, and so on up to PT. The algorithm goes with this. Let's write down the MWM guarantee. Yes, for all distributions P. We have summation T MT is less than or equal to MTP plus epsilon absolute value of MTP plus ln n by epsilon. We haven't yet decided what is capital T, what is epsilon. These are two parameters. We'll determine it this way. But let's look at each of these numbers. Now, MTPT, what is it? What is MTPT? I want to claim MTPT is exactly. What is MTPT? Huh?
Expected payout of
the row vector J. This is actually the best if I play PT, this is the best response. So this quantity over here, each thing is actually C of PT. Because the oracle is written JP, this is C of PT. So let's do now for each T. For each T, empty PT is exactly equal to CPT. You are with me on this? To put it in here, this one is actually, it's the expected value. It's an, in fact, this is in fact A PT JT, which is CPT, since JT is the best column response. Or PT. But CPT is always lower bounded by lambda star. Therefore, what do we have? But CPT is always greater than lambda star for all distributions PT. I do not care which distribution I put in there. So because of this, what do we get here? So let's make this one conclusion. So we have empty PT hence empty PT is greater than or equal to lambda star for all T. Let's keep this as 1. So this left hand side, each one is lambda star. So when you average it, it also is lambda star. What about this guy? MTP. I don't know what it is, but what I want to now keep is, let's think what happens if P. Now I'm going to use strong duality. This is true for any distribution. Let's put P to be the P star distribution. Setting P to be P star, the optimal row distribution guaranteed by strong duality. What will we have? We'll have empty P is now equal to empty P star. What is this? This is just A P star JT. Notice this is always upper bounded by lambda star. Because JT is there's a J star which will maximize this. This is a smaller response rate, so therefore this is upper bounded by lambda star. That's 2. And then the other one, empty P. I'm just going to, this is a quantity lying between -1 and 1. And when I take it with the probability vector P, this is a quantity at most 1. Since Aij belongs to -1, 1, this quantity is at most 1. Okay, let's plug 1, 2, 3 back into the our star. What do we get? We get lambda star is less than or equal to PPT, that was hand side. This is less than or equal to lambda star plus epsilon plus ln n by epsilon. Sorry, there's a by t. By t. Right. Sorry, there is no by t here. There's a by t there. Let me actually write the thing the other way around and then. So lambda star into t, the summation is less than t lambda star plus epsilon t plus ln n by epsilon. That's what I've just written that. In other words, we have nicely sandwiched this number 1 by t summation t empty pt is sandwiched between lambda star plus epsilon plus ln n by epsilon t. We want this to be delta. So let's now set parameters. So we'll set epsilon and t as follows. We'll set epsilon to be equal to delta by 2. We'll set both of them to be delta by 2 each. And what will we set t to be? We want this ln n by epsilon t to be itself less than delta by 2. So what will that be? That we want basically t to be ceiling of 4 ln n by delta square, I believe. If we set it that way, then we define lambda tilde to be the average of summation t apt jt. We have lambda tilde is sandwiched between lambda star and lambda star plus delta. So this is what we did. It has this feature. Okay. So we have got, so we can get this proxy. So we run a several probability distribution, just average them across and take the average cost vector over the things. That is a proxy for the best zero sum value. Can we also pull out P tilde and Q tilde from this? What's a candidate P tilde and what's a candidate Q tilde?
So
they want approximate mixed row strategy. So one thing to do will be actually, one candidate is actually choose P tilde to be P capital T. I don't know how to actually analyze that. I would believe that's the best. That is, as you keep going in time, PT becomes the best. What we'll actually show is actually take P tilde to be the average of P1 to PT. Yeah.
This is the part I'm confused about. So by strong duality,
Yeah.
we know that the best the best row strategy and the worst column strategy it all is standard stuff.
Yes.
So why are we concerned about P?
No. So the value of the game is you are asking why am I doing this?
Yeah.
No. I want to come up with there is the strong duality guarantees to me there is a P star and a Q star.
Yeah.
I actually want to say at the end of the algorithm, I not only lay my hands on lambda tilde, also lay my hands on a P tilde, a strategy by which the row player can play, which comes close to achieving lambda star, a strategy by which the column player can play, by which you can achieve Q tilde. Right now, I don't have P star and Q star. P star and Q star are to distribution. You only laid the value on the value of the game.
Okay,
That's the value of the game. I want to say at the end of this whole experiment, I can also tell the row player this is the strategy he has to play, and the column player this is the strategy he has to. We haven't yet said that, but I want to say that that's actually already hidden there. So one suggestion was actually use P tilde to be set to be P capital T. I don't know how to make that work. Ideally, I would think that's right. But what actually can easily be shown from what we have above is actually P tilde, define it to be the average of PT. So just define P tilde. Just define P tilde to be 1 over T summation PT. Just the average distribution across. Now let's understand why. Let's understand what is CP tilde. And I want to show that CP tilde is not too far away from lambda star. So let J star be the best column response for P tilde. So we want CP tilde. This is exactly A P tilde J tilde. What is this? This is exactly summation 1 over T the P tilde is this sum, so it's exactly A P J tilde. Now what do we know? J tilde is not the best response for PT. So we know each of this is upper bounded by 1 over T summation T A PT JT, because JT is the best response. But this quantity is exactly what we had before. This we already knew is lambda star plus delta. So CP tilde has this property. So the best column response I'm going to do is just define it to be this way. Yeah, the point is, the reason I do not know how to prove the PT is I only know things on averages. We don't have bound on a single particular, this one we know on bounds on averages, and on averages I can do this. So I can talk about P tilde being average of the PT is not the last PT. Okay, what's the candidate Q tilde?
the average QPs.
Huh? We don't have Qs at all in the picture. We don't have any Qs.
The J's that we.
So we use the J's. We see several J's. That's exactly what we'll do. We'll just build a Q tilde with just puts. If a particular J comes more frequently, we'll put that weight. So basically, it's going to be Q tilde. Q tilde, we'll define it to be Q tilde of a particular J is exactly number of T such that JT equals J by T. That's what you suggested. So and now let's see how we want to show the RQ tilde for this is good enough. So that's going to be my. So what do we want to understand? We want to understand. Actually, we would like to show. We want to show RQ tilde. This is RQ. This is Q tilde. It's not Q star. So it's certainly smaller than lambda star. We want to show it's not too much smaller than lambda star. It's only a delta smaller than this one. So let's go back to this one. So I want to recall our original statement which we had here. This statement, that was the MWM guarantee. This was true for any distribution P. So let's apply star for the distribute for the pure strategy I. Line star is the pure strategy I. What do we have? We will have 1 by T summation T MT PT is less than or equal to 1 by T summation MT pure strategy say I. So that this is just MTI. Plus epsilon by T summation MTI. These all summations are over T plus ln, what do we have? Ln N epsilon T. Now I want to look at a few things. So what do I want to say? Okay. Where is this a little white? So this quantity, the quantity over here is 1 by T summation T A. What was this? This is APT JT. That's what this is. What is that? I want to claim this is actually, what is this? Let's write down this. This is 1 by T summation T A I JT. Is that right? AIJT, and this quantity by our setting of parameters had already turned out to be plus delta. We had set it to be those two at delta. This quantity was also set to be larger than lambda star. So we have lambda star is less than or equal to 1 by T summation T AI JT plus delta. But what is this? I want to claim this is exactly R cube. This is lambda star 1 by T, not 1 by T. In fact, exactly this is AI Q tilde. Because JT is being picked according to T, therefore this is exactly AI Q tilde. I am showing that for every pure strategy I, AI Q tilde is greater than lambda star minus delta. Therefore, we have this, and this is true for the above is true. For every I, and hence RQ tilde, which is, what is it? It is max of I, AIQ tilde is also greater than or equal to lambda star. So we have got all three. That's just, you run this experiment long enough and you get it. So that's lambda. Just run it and it's expected. So this gives you, the strong duality will tell you how to, that there exists one, and MWM will actually tell you a good approximation of trying to get it. Any questions on this? So you want the statement of the theorem, but put down the statement. What we have theorem. Given any delta in 0, 1, and Oracle access to an algorithm that outputs best column response. We can O ln n by delta square calls to the Oracle approximate lambda star, p star, and q star to within additive error delta.
But the exact value, then how many calls would be?
What?
If you wanted exact value.
Oh, so this will never give you an exact value. This will never, because you see, the closer I want, I'm going to go and make more and more calls. This will never give you an exact value. So the problem with all MWM methods is they will give you things to additive error very well. But as the error goes down to zero, the number of calls are going to grow up inverse polynomially in the additive error. Is there any other ways of doing this?
No, I think this was LP.
This problem, I'm not sure whether it's NP card. No, this problem is not NP card because I think you can write this particular thing as a. You can write this as a linear program, LP, and solve it.
Yeah, but. Yeah, because
This
it's
one
only
is-
integer values.
Yeah,
It should be LP.
it is just the advantage over here. So there are certainly other algorithms which actually get you exact value. Exact. And last time, in fact, the exact value is a rational number. You can get it out of this whole process. The advantage is that those use LP solvers. LP solvers are very powerful. That is, they will use India point method or the complex or something. Whereas this one is something which we have seen the guts of the whole algorithm. We've seen every part. It's not like some black box algorithm that we are using. It's a very simple algorithm that. So, but the catch is whatever you said. That is, if you are allowed to have additive error delta, the algorithm becomes very simple. If you want to get the exact error, the exact value, you run the. This one. In fact, I do not know if I do the next lecture. So, to solve LPs itself, we will use MWM, but we'll solve LPs up to an additive factor. If you want to solve them exactly, it will be simplex or interior point methods in this one. If you are willing to allow for an additive loss, then there's a very simple algorithm. MWM algorithm is very simple. We have seen every part of the algorithm. There's nothing complicated in the algorithm at all. That's the it comes with a cost. The cost is the error. But the advantage is the simplicity of the algorithm. So possibly you get faster runtimes than doing it otherwise.
How many calls will the LP into?
Huh?
How many calls the LP will require?
The LP, that depends on the bit complexity of the payoff matrix. No, so the LP we don't have it's not even polynomial in. Firstly, LP will run in time polynomial in M and N. So it will be polynomial in M and N. This is not polynomial. This is only it's log N. So there's a huge this one. No, but even though this runs in poly with so many calls, there is a step which is linear in. Each step involves taking vectors of length n and manipulating it. But all those operations are only linear in n. They are not polynomial in n. The standard LP solver will be poly in m and n. And the constant above the exponent is not usually 1. So the advantage of all of this MWM algorithms are not going to be a replacement for existing algorithms. The existing algorithms possibly get you the right answer, but they take more time. These are much simpler algorithms and you get to see the entire running of the algorithm. We have seen, except for how the Oracle call runs, we have seen the whole algorithm. Next, we move to another application called boosting. Seen boosting anywhere? Know what boosting is? And
I've seen it in theoretical machine learning.
yeah, it's exactly the same concept. It is. So in fact, MWM for the first time it was discovered was in the ML community while boosting was discovered. That was where the multiplicative weight update method was discovered. So what is boosting?
But H and other methods existed, right?
But they all exist in the context of machine learning only, no? The hedge algorithm is a machine learning. It came in the ML community, no? Yeah. Possibly it was not boosting. Boosting, it's not Freud and Shapar's paper, but hedge existed. Freud and Shapar used it for this particular technique, for this particular application. So what is the application? Let's come. So what's the application here? So there is, we want this, we want to learn a concept. And what's a concept? A concept is just some function on 0, 1. It's some on chi is some domain, possibly a very large domain. So think of it as the standard example given in machine learning is these are chi is the set of chi is various pictures, and it tells you whether it's a cat picture or not a cat picture. And this concept is telling you want to learn, the concept is telling you whether it's a cat picture or not cat picture. So what we get to see is chi is some domain on the space of all such pictures. And what you have is you get to access, so there's some underlying, right? There's some underlying distribution. D on the concept space. What you get to see are, you get to see labeled samples according to, you have this one button, each time you press a button, you get a sample from chi and its corresponding label. You get to see several such samples. Now, after such samples, you need to come up with a hypothesis. So the learner algorithm is typically of this type. The learner gets as input several samples, CX1, X2, CX2. Huh? Sorry, what? The distribution is on the domain. So you get to you get to see random samples from the domain and also label the samples. So you're initially fed several samples from the domain, but you're also told what are the labels. So based on this, you need to come up with a hypothesis. That's your output.
Like the sample is fixed, then the label are fixed.
Huh?
If the sample is fixed, then the label are fixed. For a fixed point in the domain.
For a fixed point in the domain. So there is an underlying concept class. There's a fixed concept class, which is given a picture which tells you whether it's a cat or not. Then each time you pick a picture, you get to see several such samples and their labels. Based on it, now you come up with a hypothesis. You come up with this one, and the question is, how good is the hypothesis? The hypothesis should approximate the actual concept that you are learning. Basically, as a kid, you get to you get to see several pictures and see whether it's a cat or not, or you get to see several pictures and see whether it's a horse or not. Based on this, you come up in your mind a mental image of when I see a picture, will I say it's a horse or not? Will I see it's a cat or that's what. So there's a learner which possibly uses some extra random bits also, some other random coins if needed. So this is the standard learning model.
Does the learner know the distribution D?
No. So we'll come to that. So question is is the learner oblivious of the distribution D or no? So we are going to work in a model in which the learner actually doesn't know it. You know there's a space of pictures. You do not know what distribution it is being sampled against. So we'll also. So the learner does not know the distribution. He just gets to know there are n samples from the distribution. And then the learner comes to the hypothesis. So to be fair, now we want to actually find out what's the error of the learner. So the error of the learner, the error is going to be expected value of how many times, this is basically probability hx is not equal to cfx. But we will, because the learner doesn't know the distribution, the error will also be measured in that distribution. So you are given things from a distribution, you have to come up with some hypothesis and you have to ensure that on that distribution, which you don't know, you to perform very well. So that's important. Okay. So So we have to define the model. So variant, you follow variance definition of what's called probably approximately correct, the pack model. We'll say the learner is, we'll define two notions of learning. Firstly, we'll define what's called a strong learner. And learning algorithm A. So we'll say A is a mu delta strong learner strong learner for the concept C if for all distributions D on chi for all distributions D on chi, the error of H produced by the A, this is the error of the probability of the error being larger than mu is less than or equal to delta. And this is over the random points of A. And A runs in time, say log of 1 over mu, or let's give it one more. In time poly in 1 over delta, 1 over mu, and log of the domain size. That's a strong learner. So the algorithm, irrespective of which distribution you put on the algorithm, put on the sample, it should be able to come up with a hypothesis which works well for that distribution. That's our definition of strong learner. Huh?
Why is the rename looks like poly compared interval? Why do we could have taken from other
Typically, if you want to get accuracy delta, you would want to be, ideally, actually speaking, it should be log 1 over delta, log 1 over mu. That is, if I want error delta, strictly speaking, this delta should be log 1 over delta. If I want, well, delta is the, and one second, just me finish here. Why is it called probably? Because there's a probability of error. It's approximately because it doesn't approximately give the hypothesis, it doesn't give the right hypothesis, only it gives an approximate hypothesis. So it's probably approximately correct. And you'll see that most algorithms can run and actually, you give the confidence measure. So the confidence measure is given in terms of, you give the number. So you want to run in time log 1 over. You want everything to be run in polynomial in whatever input you are specifying. You say, I want so much confidence, I want so much. So strictly speaking, I would actually want this to be actually poly log 1 over delta, poly log 1 over mu. But right now I'm relaxing it and putting 1 over delta, 1 over mu. But this is what is this one. I don't want to actually run in time. I don't want to run in time size of chi, because then I can encode the whole truth table of chi. The learner is not doing anything. He can just have output just the truth table of concept. You want to learn the concept in a much better, faster fashion than encoding in the truth table.
these very lopsided distribution?
Yeah.
Then even in like chi step, I may not be able to learn the whole thing, right?
You won't be, so we are not, that's the whole point. We are not asking you to learn the whole function. If I'm going to give you a lopsided distribution, the inputs are also to the learner are coming from the lopsided distribution. So this is also being sampled from D.
We need to learn it.
So we are being fair to the learner. If we wanted to perform well against a particular distribution, we are going to feed it inputs from that distribution. And it has to output this only. Yeah. So you'll feed it this input, and then it's going to give we are going to, its input is going to be from the distribution, and we are going to measure its performance against that distribution. But this should happen for every distribution. And a weak learner is a very similar thing. A weak learner is in which the error of HA here error is very, very small. It's only mu. Weaker as error, the error is something, its error is just better than random guess. Let me just say. I should have just said. Let's drop the word learn. This one. This is just a learner. Strong learner and weak learner. Strong learner is mu delta. A learner is called a strong learner, where mu is typically very small. And a weak learner is half minus gamma delta learn. For some gamma 0.5. The weak learner just gets it better than random guess. So what we are going to ask is, are weak learners really weak? Or from a weak, if I construct a weak learner, the weak learner is doing something better than random. It's guessing 51% of the time on the distribution is managing to get the concept right. Strong learner means I want to get it 99% of the time. Now what you want to ask It seems as if by definition, weak learners are weaker than strong learners. Boosting is just to show, is a procedure in which we will show that if you give me a weak learner, I will convert it to a strong learner. So if you can manage to learn a concept class which is, but notice if you manage to come up with a weak learner that learns with 51% of the time, 51% of the time, but for any distribution. Remember, it's not, then I can come up with a strong learner which will learn it with 99% of the time on any distribution. It is not, this is not the same as thing for every distribution. If you come up with a learner that gets 51% of the time, I'll come up with a strong learner which also works with 99% for that distribution. I want a weak learner that works with 51% for every distribution. Then I'll come up with a strong learner that works with 99% for every distribution. I can't do it. I can't fix the distribution and don't know how to do this proof. What we'll show is if the way it is set up this way, because we believe that we don't have an underlying distribution. So the learner should be correct irrespective of which distribution. So the probably approximate correct pack model actually has this built up. That is, it says that it's a learner if for every distribution you manage to do it. Even if there's some unknown distribution, which is possibly not the right distribution you care for, it's not a pack model. It's not a pack learner. So in that sense, you can say this is unreasonable to ask that the learning you're asking it to work for every distribution in it. The reason it is set up that way is because we don't know what the distribution is it. So we ask it to work for every distribution. And we'll exploit this strength of the definition, or rather this power of the definition. So boosting will tell us, boosting is a way to say weak learning implies strong learning. Thank you. That's what we can. And this will be a consequence of two parts. One part which we'll do now, another part which will happen in 2 lectures from now. We will show that what we'll show is boosting by, what we'll show today is boosting by boosting the sampling framework. We'll assume we have a weak learner and we're going to come up with a strong learner. The way we will do it is we'll first pick n samples. So we have to construct a strong learner from, we have to construct a strong learner. This is what we want to do. So what I will do, this one, strictly speaking, a strong learner has to work on the entire distribution. What we'll do is we'll just do the following. We'll first pick n samples, x1 to xn. Each of them construct a strong learner for the distribution D. This is what we want to do. We will pick n samples from the distribution. And what we'll come up is we'll come up with, and we also have the labels of this sample. You see, comparative to what I'm going to do, I'm going to come up with an algorithm that will correctly label this on all but a gamma fraction of points. And we'll show, of course, there's an easy way to do it. I have the samples with me. I can truth table put it out there. But we'll say that this algorithm actually has complexity much, much smaller than capital N. N is one way to do it trivially is to write it in terms of capital N. So we'll show that for every N, there exists an algorithm that will, that's what we will show. We will construct an algorithm that will label the samples on these guys correctly with probability at most gamma. And we say that if you can do this, 2 lectures from now, we'll show that we can do it for the whole distribution D on chi. So we'll come up for this. So given n samples, capital N samples, from D. Will construct a simple algorithm. The simple will be important. It will not depend on capital N. That will be the whole point. That misclassifies at most a gamma fraction of these samples. And the simple will not be a function of n, it will be this one. Later on, we'll show that if you can do such a thing for every sample of capital N, if you can come up with an algorithm, then we will be doing VC dimension later on, of course, later in the course. We'll be discussing VC dimension. And when we discuss VC dimension, what we'll see is this algorithm will be simple. We'll actually quantify what simple is. Simple will be in terms of the VC dimension of this algorithm. We'll show that if we manage to come up with an algorithm whose VC dimension is low for every sample of size n, then we'll extend it. We'll be discussing and then show that an algorithm with VC dimension less than D that works, that misclassifies most gamma fraction of a sample set. Let's show that if an algorithm, then the algorithm can be extended to entire chi, provided D and are all small. We'll see this later on. So for now, we will defer this because I'm not even talking what VC dimension and n and all. We'll just look at this problem. Okay. So what do we have here? We have n samples. We also have their class. We have their labels. We have C of x1, C of x2, C of xn. In particular, we can run the weak learner on it. When we run the weak learner on it, it will give you a hypothesis that works well on half plus. What did I call it? So no, that's why I don't want it. I wanted it to be mostly mu fraction. Yeah. So what does the weak learner do? If I run the weak learner on x1 to xn, it's going to give me a hypothesis that is going to be correct on half plus gamma fraction of the inputs. If I run it on the uniform distribution, if I could notice the weak learner works on any distribution on it. So in particular, now I could put an arbitrary weighting on the samples x1 to xn, and depending on that, I can change and run the weak learner on that distribution. It will classify half plus gamma fraction according to that distribution. So we have this extra power. The weak learner is going to give me for any distribution that there is an underlying distribution D. That's the distribution is fixed now. What I'm going to do right now, I have picked n samples from it, and thus from those n samples, I can feed the weak learner whatever distribution on those n samples I want to get. We will do various distributions. We are guaranteed that the weak learner for each one of them will correctly classify a half plus gamma fraction of inputs according to that. So we collect all these weak learners together and come up with a strong learner which will actually correctly classify all of x1 to xm with making error at most one mere fraction. We will use the fact that the weak learner performs well on every distribution on the n sample points. And we'll do this. Okay. So what is going to be, we're going to, for the setup for the, what's going to be the MW epsilon setup. The n experts are in fact going to be the m points. Each point is going to be an expert. So x1 to xn is going to be what I'm going to call as the expert. So our distribution is going to be some distribution on the n. Initially, we'll start off with the uniform distribution P1, which will be uniform, and we'll be changing this over time. So we have to specify this. We have to also specify the cost vector. So MT. MT previously in index with x, so I'm going to index with x. Index with I, it was an expert. I'm going to index with a particular x, which is this one. What should be the cost vector be? So notice, so let's run this. So let's do this algorithm. So we are going to, that's going to be, let's see this point. So PT is a distribution on these n samples. Okay. PT is a distribution on these samples. So start with P1 being the uniform distribution. Okay. P1 to be the, yeah, let P1 be the uniform distribution. What does a weak learner give me? Weak learner gives me, if I run weak learner on PT, what do I get? I get a hypothesis HT. Outputs a hypothesis. Outputs a hypothesis HT satisfying. What does it satisfy? The probability that HTX is not equal to C of x when I pick x according to PT. This is certainly less than or equal to half minus gamma. Equivalently, expected value of HTX minus C of x when x is picked according to PT. This is, that's what the weak learner is going to guarantee me. Now, I need to tweak the probability distribution in such a way such that I can, so the weak learner is going to ensure that on half plus gamma, it's going to get correctly. Initially, uniform distribution. Now I have to come up with a cost vector so that I'm going to classify almost everything correctly. So the question is, what is the cost vector we will use? Think of a cost vector. I'm going to use, let me write it down and then tell me why this cost vector makes sense. So there's a hypothesis, that's the hypothesis being revealed at the time step T. And this, what is this? This is 1. If the hypothesis gets it correct, it is 1. If the hypothesis gets it wrong, it is 0. Notice it's working the other way around. the cost vector. And the reason is anything that gets it correct, those x's I'm already got it correct. So I need to put weight on the x's which are not got correct. So I need to skew the distribution towards x's which have not got it correct so far. And therefore this sort of cost vector actually helps me. So each time I get the answer, I look at what the answers are. And I look at all the things on which I got it correct. Things which I got it correct, I'm going to reduce the weight of. So the distribution is going to increase its weight on the things which it gets it wrong. So each time what happens is it puts more and more weight on the things which I've got it wrong. So that eventually at the end of it, I'm hoping that the things in which I got it wrong totally is actually very little. Okay. So once I've done these two, the MWM has been fully set up. So I have done I told you what's the starting distribution. I told you what PT is. PT is a distribution of n samples, and I told you what the cost vector is. So we can run MWM except for the parameters epsilon and t. We'll define what that is later on. So let's just run MWM for t steps. And let H tilde be the major. So we have several hypotheses. Let's take the majority of the hypothesis. Capital T. So each hypothesis is a Boolean function. H tilde is the function which is the majority of. For every input, it takes the majority value what all these guys gives and tells that. I want to say H tilde actually classifies extremely well on the n input space. So let E be the error set of H tilde. That is the set of X belongs to the sample set. Yes, this was the sample for me. Yes, the sample set. H tilde X is not equal to C of X. And our goal is to show size of E by size of N is less than or equal to mu. This is what we want to show. Okay. So we have only one thing. Let's just write down the MWM guarantee on this. What do we have? We have summation T MT PT is less than or equal to summation T MTP. So because this is 0, 1, I can actually put 1 plus epsilon summation T MTP. I would use the divergence form P by P1 by epsilon. Okay. Let's stare at each one of them. What is MTP? How did I define MT? MT was exactly, it gave you the PT was the distribution you used at the time, each step. MT was this cost vector defined this way. So MT is going to, so whenever you get it correct, it marks it 1, otherwise 0. So for every PT, we know that since MT measures the quality of the weak learner, I want to claim MTPT is actually greater than or equal to half plus gamma n.
So that
Not just half plus gamma. Because for that distribution, it's 1 if you get it right and it's 0 if you don't get it right. And you're claiming it's a weak learner. Therefore, this is exactly the probability with which you're getting it right. This one. Rather, let me I want to say MTPT is probability over X coming from PT HT does not err on X, if you recall, because the way we had defined it. If it does not err, you can get 1. And if it errs, you get 0. Therefore, this quantity is at least half plus gamma. Okay. This is true for every distribution P. So let us choose a distribution. Let us choose a distribution that is uniform on E. That is the set H tilde error zone. I want to claim for each X in the error set. Let's look at this quantity. Let's look at summation T MTX. What is this going to be? These are the error set. Empty is X is the fact that the teeth hypothesis gets it correct on X. So this is at most T by 2 because it's the H tilde is the error set and the majority error set. Therefore, this is less than or equal to T by 2 for each one of them. Since E is defined as the set H such as H tilde is not equal to C of X. Which means that at least the majority of them should have got it wrong. Therefore, the number of correct things should be at most T by 2 for each of these X's. So let's go back to this one. So this one, what we got was, this is half plus gamma times capital T. What is this? This one, if I put my weight on just the P guys, this is always P by 2. What did I want to say? No, what did I want to say? So so what I want to say is, at the end of this, plugging 1 and 2. On time, but we'll be done in 2 minutes. Plugging 1 and 2 into star. What do we have? So this one, MTPT is always greater than half plus gamma. If I plug this over here, I get half plus gamma times T is less than or equal to. This one, it's 1 plus epsilon. This is always, if P is supported on the error set, that quantity always is summing up to T by 2. So this is less than or equal to T by 2 plus D P P1 by epsilon. Sorry, there is a 1 plus epsilon sitting in front of you. Okay. Let's write this again. This is half Let's, what do we get here? This is, you get the, so T by 2, I'll bring in half plus epsilon by 2 the other side. So I'll get gamma minus epsilon by 2 T is less than or equal to D P P1 by epsilon. What is this? This is summation over X in E. It's a uniform distribution on E. So that is 1 over E ln 1 over E by 1 over N. So this is summation Pi log ln Pi by Qi. Pi is supported only, P is supported only on the error set. Therefore, summation of X over E, 1 over E, that's the probability, times ln 1 over E on 1 over N. So this quantity is exact by epsilon over here. So this quantity is 1 over epsilon times, what is it? It's just ln N over size of E. Move things around, what do you get? You get size of E over N is less than or equal to, what happens once I'm going to mess over here. Let's see. So let's set gamma to be equal to epsilon. So if you set gamma to be epsilon, we get epsilon by 2t, rather epsilon to be equal to gamma. That's the setting. We haven't yet set the parameter for this one. Epsilon by 2 gamma t, rather I want it to be gamma by 2. So I get gamma by, which one do I want to set it? Gamma by 2t is less than or equal to 1 over gamma ln N mod E. Well, got it right. Exponential, right? So what do we get? We get x spin gamma square by 2t is less than or equal to N by mod E. So our fraction N by, what did we want to bound? We wanted to bound mod E by N is less than or equal to x spin minus gamma square t by 2. So you just set is less than or equal to mu by setting t to be equal to, what should t be set? Set equal to ln 1 over mu 2 by gamma square. Just set t to be that, we'll get it. So basically what's happening. So all of this was just a calculation. What am I saying? So you running t 2 by gamma square ln 1 over mu weak learners and averaging their performance yields a strong learner. So in other words, the strong weak learner was only getting it right with half plus gamma. From half plus gamma, we went to something which got it correct with 1 minus mu. By just running it constantly, so you run the weak learner a constantly many fraction of times and you manage it. It's actually a very simple repetition of the weak learner. It's not from truth table form this one. It's a very simple, and that gives you the boosting algorithm. Okay. So this is Weak learning is the same as strong learning, provided the weak learner can work against any distribution. That's the key fact. If the weak learner was working only one distribution, I do not know. I'm using the fact that on every distribution, the weak learner is getting it correctly. That's key to it. Okay, we'll stop this. I'll do 2 more applications next week and on Thursday, then we'll wrap up this module.